Welcome to ClockFabric Electronics Academy. Here we will study electronics and computation from an inventor's perspective. In this video, we will introduce our viewers to the Intel Cyclone 10 LP FPGA Evaluation Kit. We'll do the unboxing under the camera and consider the most prominent components present on the board. In the end, we'll put together all the components in one slide and create a highly simplified board block diagram that we'll be referring to throughout the course. My name is Bard and I'll be the host for this video session. In 2015, Intel acquired Altera. After the acquisition, the latest offering from Intel and Altera in the line of FPGAs are the Cyclone 10 family of FPGAs that were announced in the year 2017. In the same year, Intel also launched Intel Cyclone 10 LP FPGA Evaluation Kit for the FPGA developers to start experimenting with the latest product. Intel Cyclone 10 LP FPGAs are optimized for low static power and low-cost applications and are fully supported by Quartus Prime software suite. Based on the price point at which the evaluation kit was released and availability of a much more accessible toolset, that is Quartus Prime Lite Edition, which can be downloaded without having to buy a license, it looks like Intel is planning to improve on FPGA technology and bring it to a much wider audience. And with courses like this and a much more open ecosystem, we believe Intel will succeed in bringing this technology to the masses 98.75% guaranteed. At the end of this course, we are confident that our viewers will be motivated enough to integrate FPGA into their next project and realize its full potential. They should also be able to scale up to bigger and more complex designs using Intel Quartus Prime Standard and Pro editions without any difficulty. So these are the reasons we chose to use Intel Cyclone 10 LP FPGA Evaluation Kit as our development platform for learning the FPGA technology. Without further ado, let's do the unboxing now by switching on to the camera. So this kit came in a very nice package. This package itself shows that Intel plans to reach a much wider audience regarding this kit because it looks like this kit could be hung on the shelving at a retail store. We got ours from Mouser.com. Saying that, let's open the box now. Here we go. This here is the board itself. Let's set it aside for now. This is the Y cable that we will talk about later when we consider the power supply options and development. There are also some documents present in the package which we will look into right now. The first one looks like some kind of MSDS document which we will have to consider before disposing of this board. The second one is kind of important, considering safety and regulatory information. The third one is a quick setup guide which also provides a link to its official website. Okay, now let's come back to the board. This little label hanging around the board contains a guideline saying that this board is for evaluation only and can be used only by product developers, software developers, and system integrators. Now let's get rid of that. On the screen, we can see two high-resolution snapshots of both top and bottom faces of the board put together side by side. These are the pictures we'll be using while we study the components present on the board. Oh, before we start, we would recommend our viewers to grab a cup of tea or their favorite beverage because it's going to be quite a ride. So the most noticeable component on the board is of course the Cyclone 10 LP FPGA device itself. On the screen, adjacent to the snapshot of the real chip on the board, we have created this highly generalized topical view of the FPGA device and its pin arrangement along with the I/O bank position. For a more detailed assignment, we will refer to the board schematics when we start using this chip. For now, let's have a brief overview of the Cyclone 10 LP FPGA device present on the board. It's a 256-pin UBGA package and the I/O pins are arranged in 16 by 16 grid array at the bottom of the chip. These I/O pins are intrinsically grouped into 8 groups, also referred to as I/O banks, and each I/O bank in the device has a separate power bus. The I/O banks at the sides 1, 2, 5, and 6 are also referred to as row I/O banks. Similarly, I/O banks at top and bottom 3, 4, 7, and 8 are called column I/O banks. Only the column I/O banks support the 1.2 volt HSTL Class 2 I/O standard. while all I/O banks support all other single-ended and differential I/O standards that are supported by Cyclone 10 LP device. These details come in handy when we start interfacing other peripherals to the board. In the realm of FPGAs, one of the key features that dictates the overall personality of the device is the logic element count, which tells us how complex of a logic can be programmed on that particular device. This device has 24,624 logic elements. This device also has internal memory that is composed of memory blocks which can be configured as RAM, FIFO buffers, or ROM. This device has 66 M9K memory blocks with a total M9K memory block capacity of 594 kilobits. It also has 66 18x18 multipliers, which will enable us to implement custom DSP blocks within the device. It has 4 independent PLLs to drive 20 clocks, which will in turn drive the internal ClockFabric within the core. So that's where our channel name ClockFabric comes from. Out of 256 pins, 150 pins can be utilized as I/Os and 52 out of them support low voltage differential signaling or LVDS. The core runs at voltage range of negative 0.5 volts to positive 1.8 volts. By default, it has been set to positive 1.2 volts based on the board configuration. The input clock frequency supported by this device is in the range of 5 MHz to 472.5 MHz. There is so much to this FPGA device. That's why we will consider its architecture and core fabric in a separate video. Since all the programmable logic in the chip is controlled by the clock, let's consider the clock sources provided by the board next. This here at the back of the board is the SI510 50 MHz crystal from Silicon Labs, which acts as a dedicated source of clock for the PLLs present in the FPGA device. Based on the schematics, 250 MHz clock output from this crystal, CLK-P1 and CLK-N2 are routed into Max10 FPGA as M10 CLK50M and to Cyclone 10 LP devices I/O Bank 1 as C10 CLK50M respectively. Once again, here at the back of the board, we can see this chip from Silicon Labs. This is a programmable clock generator coupled with this 25 MHz crystal. The frequency outputs from this chip can be controlled by interfacing to it via an I2C port. The best thing about this board regarding this programmable clock generator is that Intel provides a GUI application to program this chip, so that we can configure the clocks coming out of this device before we start writing our FPGA logic. Based on the schematics, this programmable clock generator has 3 clock outputs, CLK0, CLK1, and CLK2. These clock signals, after they come out of the chip, are routed to the Cyclone 10 LP as CLK0 as ENET CLK125M to I/O Bank 3, CLK1 as C10 CLK-ADJ to I/O Bank 6, and CLK2 as HBus CLK50M to I/O Bank 5. By default, their values are set to CLK0 at 125 MHz, CLK1 at 100 MHz, and CLK2 at 50 MHz. After the clock sources, let's consider the external memory devices installed on the board. This here is one of the 2 external memory devices present on the board. This 128 megabit memory chip from Synaptic Labs supports HyperRAM technology, which is controlled by Hyperbus controller, also known as HBMC. The 8-bit Hyperbus pins coming out of this chip connect to I/O Bank 4 of the Cyclone 10 LP. We will talk about this chip and the HyperRAM technology in a separate video. For now, let's just say that this part of the memory can be used as RAM for the processor core that we will implement in our FPGA later. Now let's consider the other external memory device present on the board. Here is the 64 megabit Intel EPCQ flash memory chip. This memory chip will be used to store non-volatile configuration data, board information, test application data, and user code space along with factory reset configuration data. This is a low pin count device. Data and control pins coming out of this device are connected to I/O Bank 1 of Cyclone 10 LP. One interesting feature of this device is that data can be uploaded to it directly using serial mode. This way, configuration data can be uploaded without having to bother with the FPGA device itself. This configuration data can later be loaded into the FPGA device using an active serial mode to program the logic. After the memory device is present on the board, let's explore various connectors and interfaces exposed by this board. This here is the 2x20 pin GPIO expansion header present in the board with 36 GPIO signals. These pins are all 3.3 volt single-ended LVC-MOS LVTTL signals which are connected to Cyclone 10 LP directly. There are also one 5 volt, one 3.3 volt and two ground pins present on this header. We will interface various external peripherals using these pins for our projects later. This board also features Arduino UNO R3 type connectors. These connectors are compatible with most Arduino shields, but one thing to keep in mind is that only the 3.3 volt compatible shields should ever be connected to these headers or will risk damaging the FPGA. All the digital I/O pins from these headers are connected to Cyclone 10 LP device pins. The analog pins come from a different source, which we will discuss later. This here is a 12-pin Digilent PMOD compatible connector which can be used to connect various low-frequency, low I/O count peripheral modules, also known as PMODs. It provides 8 I/O signal pins which can offer current up to 250 mA at 3.3 volt when the board is powered from external power adapter. As a communication device, this evaluation kit features one Ethernet port via RJ45 connector. There is this LAN transformer from Worth Electronics between the RJ45 connector and MAC to PHY interface implemented using Intel Axway Gigabit Ethernet technology. This chip here is the physical layer transceiver from Intel, which is configured to interact with the FPGA via RJ-MII interface with MDIO/MDC interfaces as the management front. This 25 MHz crystal provides clock to this transceiver chip. This particular MAC to PHY implementation is specific to Intel Cyclone 10 LP FPGA Evaluation Kit, which we will discuss in detail in some later video. The Ethernet RJ-MII interface connects to the I/O bank 8 of the Cyclone 10 LP FPGA. This board also features several LEDs, switches, and buttons. These three green LEDs are used as Ethernet link status and speed indicators. This blue LED here is used to monitor the power status of the source. It turns on when the supplied power is within range. This yellow LED indicates the FPGA's configuration status. It does not glow if the FPGA has not been configured properly. Apart from the aforementioned status LEDs, this board also features 4 green user programmable LEDs. These LEDs maintain a direct connection to the FPGA pins so they can be used to test the designs. This switch here, called the JTAG VTP bypass switch, is used to enable or disable direct JTAG programming of the FPGA. That means that this board can be programmed using the 10-pin JTAG header when this switch is pulled to write enable. These 3 switches marked as SW1.1 to SW1.3 are user programmable DIP switches. Now let's look at the buttons that are present on this board. This button here, marked as conf, is the reconfiguration button. Press this button when the power is on to reconfigure the FPGA device. This button here is the reset button. Press this button to initiate a device-wide reset when the board is on. These 4 buttons marked as S3 to S6 are user programmable buttons. These user programmable LEDs, switches, and buttons will come in handy while testing our designs in the future. There are several voltage regulation and power management chips present on the board. All these power SoCs are responsible for providing several voltage references to onboard components. In fact, there are 4 Intel Empreon power SoCs present on this board. At the top face of the board, we see this EN5329QI, which provides a 1.2 volt reference at max current of 2 amps. Similarly, the EP5358HUI present at the top provides a voltage reference of 1.8 volt at 0.6 amp max current. If we look at the bottom of the board, we see this EN5339QI that provides a reference voltage of 3.3 volt at max current of 3 amps. Another EP5358HUI, also present at the bottom, provides a voltage reference of 2.5 volt at max current of 0.6 amp. At this point, we have introduced almost all the components present on the board. Now it's time we consider its programmability. The Intel Cyclone 10 LP FPGA Evaluation Kit supports two configuration methods. It can be configured by downloading a .sof file to the FPGA, which when reset or reconfigured will power on to a blank state. The other method is to write a .jic file to the EPCQ flash, which when reset or reconfigured will configure the FPGA device from the flash memory via active serial mode. This board also supports two different methods to download these files. The first method uses inbuilt Intel FPGA download cable 2, which is implemented by onboard Intel Max 10 FPGA device and the USB controller via the USB Mini Type B receptacle. We will discuss the Max 10 chip in a while. Just to avoid any confusion pertaining to the FPGA download cable 2, it was formerly known as USB Blaster 2. The second method of downloading a configuration file to the board involves this 10-pin JTAG header present on the board via some external programmer. There are three diverse types of external programmers that could be connected to the JTAG header, namely Intel FPGA download cable, Intel FPGA download cable 2, and Ethernet Blaster download cable. Now let's look at this chip here. It is Intel Max 10 FPGA device pre-configured to act like a microprocessor. It is in fact a highly capable device with built-in ADCs, NEOS to software embedded processor support, DSP blocks, and soft DDR3 memory controllers. It also comes with dual configuration flash options, enabling dynamic switching between two configuration images on a single chip. This Max 10 device has been pre-configured and locked at the time of manufacturing to host the FPGA download cable 2 and provide ADC functionalities to the analog pins present in the Arduino headers and a few other minor functionalities. Still, we think Intel's decision to use one FPGA device to configure another FPGA device instead of some other microcontroller is really inspiring. This Max 10 FPGA device interfaces to the Cyclone 10 LP's JTAG pins located at I/O Bank 1 to ultimately upload the configuration settings to it. And on the other end, it is initiated either by this USB controller from Cypress Semiconductor via USB or by these JTAG header pins with the help of some external programmer. This 24 MHz crystal provides a clock to the USB controller. This 10-pin JTAG header interfaces with Max 10 FPGA directly by skipping the USB controller, which in turn writes the configuration settings to the Cyclone 10 LP. But as we have mentioned before, for direct JTAG programming, the JTAG VTP bypass switch must be set to write enable. We will see how this works in a later video. By providing two power supply options, this board is flexible in terms of power supply as well. The first is 5-volt power supplied through the USB. This USB-Y cable that came in the package has these two USB-A jacks at one end, which are meant to be plugged into the computer at the same time. The black one provides power and USB functionality, and the red one provides power only. So both of these USBs combined provides about 1 amp, which is enough current for most applications that doesn't have to power external peripherals. But if we decide to use Arduino Shield or connect high power peripherals to the board, then the 5-volt external power should be provided through the onboard 5-volt DC barrel jack. Any 5-volt DC power adapter will work, keeping in mind that it can provide enough power to the peripherals connected to the device. Intel recommends 5-volt DC with 3 amp current. This board implements an O-ring circuit to select a suitable power source depending on the power requirements of the board. At this point, we are done introducing all of the visually prominent components present on the board. Just for the sake of completion, this board also contains various SMD components like these op amps from Microchip and these current sense amplifiers from Linear Technology to enable the board's overall functionalities. So that's all for the unboxing and brief introduction of the board. Before we leave, let's put all the components we just discussed up until now into one slide and present the overall high-level schematics and the board block diagram. This will be the block diagram that we will be referring to throughout this course. We will peek into the full schematics only when we need it. We have also converted this block diagram into a PDF file which can be downloaded from our GitHub page by following the link below. We hope our viewers found this video helpful. If any comments, don't hesitate to leave them below. In the next video, we will install the toolsets, plug in the board, and run the board test system. So long for now.